All right, so now we know how to deal with data types. And now the question that comes up is, there are certain operations that we want to perform on our data. And sometimes it's the same operation for different types, like the example of I plus j versus x plus y there. And so somehow or other, we have to have different versions of plus and know which one to use. And that's the problem we're going to be addressing for the rest of the week. But operators that have two operands, like plus, are fairly complicated. And I like to make things simple. So I'm going to start with a different example of data types and operations. And I'm going to make a little chart to show you what we're doing. My types are geometric shapes. So I have, think of it this way. Square and circle. Whoops. And the operations I'm going to do are perimeter and area. Okay? Now, what goes in the boxes? A formula, right, for how to do that. So for a square with side S, what's the perimeter? 4s. What's the area? S squared. OK, for a circle of radius r, what's the perimeter? 2 pi r. And what's the area? Pi r squared. Great. Except I hope that you understand by now that I'm not really going to do it quite like this. I'm not going to put formulas as pieces of text. What I want to think about is functions. So I'm going to think S maps to 4s, S maps to s squared, R maps to 2 pi r, and R maps to pi r squared. OK, so that's what's in my head. So for this simple example of two data types and two operations, I have 4 procedures. OK, now think about integer, rational, real, complex, plus, minus, times, divide, integer, rational, real, complex. So there's 2 data types involved, left operand and right operand, and 4 possibilities for each of those, and 4 operations for a total of 4 times 4 times 4 is 64 functions we have to keep track of. OK? So that's already a pain in the neck, and that's, there are more types and more operations than that. So that's why I'm starting with a simple case. But I want you to understand that the subtle mechanisms we're going to invent for dealing with this problem are worth inventing, because real problems are more complicated than the ones I'm showing you today. OK? So the first thing is let's make some data with type tags attached. So I have procedures make, square. Whoops, I'll do that. What I want to do is define S4 to be make square 4. And the value of that, just to make it clear, is a pair whose car is the type tag and whose gooder is the value. And I'm going to say I'm going to say define C4 to be make circle 4, and define S5 to be make square 5, and define C5 to be make circle 5, just to have a little data around to play with. And now we're going to look at how to organize all this information about the methods for doing some operation on some data type. Okay? And there are 3 ways we're going to look at doing it. And the first one, the book calls conventional style. It's called that because it's kind of the obvious way to do it. That's what people did for a long time before computer scientists came around to, try to improve things. Namely, it goes back to that thing I keep talking about nouns versus verbs. And when you're thinking about how to do an action, the most obvious thing for people is to organize their thinking around the verb. Right? So here's how to build a house. And within that, there's how to build a house with a wood frame, and how to build a house of masonry, and how to build a house out of plastic prefab panels, and so on. And it's all under the heading of how to build a house. Okay? So up here, we have a procedure area that takes one of these shapes as its argument. And it says, OK, what kind of thing am I looking at? Am I looking at a square? So that's this question right here. So is the type tag of the thing I'm looking at the word square? If so, I'll just return contents of shape times contents of shape. Contents is the number that represents, in this case, the side of the square. So if I say down here, area of S4, I get 16. Area S5, I get 25. Right? The side of the square of the side of the figure. Okay, if not, then is this a circle? If so, the area is pi r squared. So if I ask for area of C4, I get pi times 16, which is about 3 times 16, which would be 48. This is 50, close enough. Area C5, I should get something around 75 or 80. Yep, there we go. Okay? Any questions about how this works? Great, this is the easy one. So on my picture, this is conventional style, where we group things basically by the columns. So everything having to do with a particular verb, find the area, all the different ways of doing it for the different data types are grouped together. Okay? Well, that's not so bad, is it? It's straightforward to write. It does do the job of sort of grouping the ways of doing something together so you can find them. You don't have to dig through 64 different little procedures. So that's all fine. The only problem with this is, whoops, if I decide later on that I'd also like to be able to deal with regular hexagons or spheres or triangles or something, I'm going to have to go into code I've already written and edit it. I'm going to have to edit my area procedure, and there's the similar perimeter procedure here that has the same structure. And I'm going to have to find all of those things and put in an extra cond clause for whatever shape I want to add. Now, the trouble about going back and editing procedures you've already written is that you introduce bugs. And anytime you write code, you might introduce a bug in your new code. But here you run the risk of introducing bugs into code that used to work. For example, by getting the parentheses wrong. okay, by putting your new clause in the wrong place, like inside one of the existing clauses or something like that, would break code that used to work. So whenever possible, our goal is not to ever have to go back and change working code in order to add new features. So that's something to remember about designing a program.